Alright, silly people, here's the situation. We're going to be proving some stuff about the eigenvectors and eigenvalues of unitary matrices through some tomfoolery. So, the first thing that we have to prove is that u alpha with u beta, the inner product of those, is equal to the inner product of alpha with beta. And I think it's a lot more reasonable to write this out in a different notation because ket of u alpha is just u, it's the dagger of u alpha, right? Times u beta. Okay. Uh, and then if you take the dagger of u alpha, you get alpha star, or not alpha star, alpha is a vector, so it needs to be alpha dagger times u dagger, and then it's times u beta. And look at that. Uh, you have that u dagger times u is equal to 1, considering that they're unitary matrices. So this is equal to alpha dagger beta, which is actually just the same thing as alpha with beta. So yeah, these are all equal. This is a true statement. Easy. Next bit is to find, or that the eigenvalues of a unitary transformation have modulus 1. That is, if you have that u times alpha gives you just an eigenvalue that I'm going to call lambda times alpha, then the modulus of that lambda is equal to 1. That's a pretty crazy idea. Uh, but the way to prove this really quickly is to take the Hermitian adjoint of both sides of the equation, but first of all by writing it in the notation of without the bras and the kets, just lambdas and u's and alphas, but then take the Hermitian adjoint of both equations so that you get u or alpha dagger u dagger equals lambda star alpha dagger. And then if you call this equation 1 and this equation 2, you multiply 2 times 1, and so you get that alpha dagger u alpha equals lambda star lambda alpha dagger, that's supposed to be a dagger there, alpha. And so that's pretty cool. But then u dagger u is 1, like we said before. So we have that alpha dagger alpha equals lambda star lambda alpha dagger alpha. And if we wanted to put it back in bracket notation, we would say inner product of alpha with itself is equal to lambda star lambda inner product of alpha with itself. But the inner product of any vector with itself is equal to 1, right? So we have 1 equals the mod squared of lambda. Take the square root of this equation, and you get that 1 is the equal to the mod of alpha. So this is a true statement as well. Finally, we need to show that the eigenvectors of a unitary transformation belonging to a distinct eigenvalues are orthogonal. That's a lot of words, but that means that if you have two eigenvalues now, so two eigenvector equations, so u ket alpha equal to arbitrary eigenvalue lambda times ket alpha, but also u times ket beta is also equal to arbitrary eigenvalue mu times ket beta. Does alpha with beta equal 0? This is a pretty funky little thing to do. One thing that you can do is you can go ahead and think about alpha u beta, or let's write it in a sensible notation, alpha dagger u beta minus alpha dagger u beta, that equals 0, right? These things would cancel out. But there's two different ways to approach the expansion of this. The one of the ways that I'm going to do on the one on the left is group this together because alpha dagger u is just the Hermitian adjoint of alpha, or it would be u alpha, it'd be u dagger alpha dagger times beta. And on the one on the right, I'll just use the eigenvector equations to say that u times beta is mu times beta. So we've got mu alpha beta on the right. Okay, what is u dagger alpha? That's an interesting thing as well. So what I'm going to do is I'm going to do this in a different color first of all. And I'm going to move this guy down here and say, oh, if that's true, then u dagger u alpha is equal to lambda u dagger alpha. And then u dagger u is 1. So we have alpha equals lambda u dagger alpha, right? In other words, you can move that lambda to the other side because it is just a number. You could say lambda alpha equals u dagger alpha. Now remember in the last part of the problem where we proved that lambda star lambda equals 1? Let's use that. Let's multiply the left side of our equation by 1. And by multiplying by 1, I mean multiply by lambda star lambda. So you get that sort of thing equals u dagger alpha. Then the lambdas cancel out. So you get lambda star alpha equals u dagger alpha. Or in the notation where we don't have kets, it's lambda star alpha equals u dagger alpha. Let's put this into our equation up here that we know should be equal to 0. So we have that u dagger alpha now is lambda star alpha, and then that's in a dagger, times beta minus mu alpha dagger beta equals 0. If you take the Hermitian adjoint of this stuff now, you get that it's alpha, or it's lambda without a star times alpha dagger beta minus mu alpha dagger beta. Cool. We can rewrite alpha dagger beta now as the inner product of alpha with beta and group them together into a term proportional to lambda minus u equals 0. And since from our two eigenvector equations, the stated assumption, or I guess non-stated assumption, was that lambda is not equal to mu because they obey different eigenvector equations. So if this is not equal to 0, then this should be equal to 0 for this equation to work. So that means that alpha beta is 0, which is what we were trying to prove in the first place. So, good stuff.